Hi, I'm Vince Weaver, an associate professor at the University of Maine, and I'm here today to talk to you about Sizecoding on the Apple II. As an aside, I have a side project where I took the same program and size optimized it for 30 different architectures a while back. I need to get back to it and re-optimize 6502 code. You can check that out. But today I'll be talking about specifically the Apple II architecture. So, the Apple II was first released in 1977, one of the original 1977 Trinity. Commodore pet people like to say they were first, and while it's true they were the first ones you could pre-order, the first you actually could buy was an Apple II. It has a 1 megahertz 6502 processor in it, from 4 to 48K of RAM, a discrete 7400 series logic in it. You load the stuff off a cassette tape, a bit-bang speaker, a 40 by 24 text mode, a 40 by 48 15 color low-res mode, a 140 by 192 6 color high-res graphics. You did need to have at least 16K in your system for graphics, and it had Woz's integer basic in ROM. The Apple II Plus came out in 1979, an update. Mostly it had 48K RAM standard, and by then most people had 140K 5¼ inch floppies, and the basic was replaced with Applesoft Microsoft Basic in ROM. Apple IIe came out a bit later. By now 64K RAM was standard, you up to 128K. Finally had lowercase letters. 80 column card was standard. If you had 128K, you can get some fancier graphics modes. Apple II Enhanced came out a little bit late after that. It had a 65 CO2 processor in there now, which had some more advanced, more compact opcodes you could use. But if you used those, you weren't backwards compatible with the older systems. 128K of RAM, and had mouse text, which was extra characters, text characters for drawing text GUI-like applications, sort of Mac-like applications. They weren't very useful for ASCII art. Apple IIc came out, 6502, as a sort of portable system. It was mostly backwards compatible. You could also get a 2C Plus with a built-in accelerator to run it faster. And finally, the last Apple II is the Apple II GS. This is actually a 16-bit system with a 65C816, which is actually the same chip that was in the Super Nintendo. Much more advanced, much better graphics, much better sound, including a sound chip by the guy who did the Commodore 64 SID chip. This is a whole other story, whole other optimization task, so I won't be covering this in this talk. So the first thing with Apple II optimization is, of course, optimizing for the 6502 processor. And there's some typical tricks for that. Some simple ones are counting your loops backwards, usually saves a byte. The bit trick, where you can skip over things by putting them inside the bit instruction. Putting your data encode in the 0 page. Using the X and Y registers whenever possible. Self-modifying code. And when all else fails, you can give them an Ask Cucumber, who is the famous Apple II 6502 size optimizer, who can usually shave a byte or two off pretty much any program that you can send him. Over there with me is Chuck Peddle, the lead designer of the 6502 chip. He's actually an alumnus of the University of Maine, and we actually got him to come visit a few years back. So, Apple II specific optimizations. So like most 6502 systems, 0 page is at page 0, the stack's at page 1, you have some free space, and then a low-res graphics has 2 pages you can view, one starting at 4, one starting at 8. Some more free space, and the high-res pages are starting at page 20 to page 40, and page 40 to page 60. We got some more free room, and then DOS, or the operating system, was a little higher. Starting at C0, that's where the I/O and the soft switches and the expansion card ROMs go. And after that, starting at D0, you have the Applesoft ROM, the basic ROM, and then at the end you have the monitor ROM. And you can use some of those routines there to write some compact code. So as a review of the text and low res, they live in the same spot. 1 kilobyte starting at address hex 400. In 6502, you use $sign to mean hexadecimal. So it's a low res 40 by 48 15 color mode with, you would say, why not 16? Well, the 2 grays are identical, or at least it's complicated, but you can view them as identical. And optionally, you can flip into the bottom 4 lines of the screen, 4 lines of text for the bottom of the screen. You can turn that on or off. The text mode is 40 by 24, no color. You can get normal text, flashing text, or inverted text. On the 2 and 2 Plus, you only get lowercase. There's no box or line characters, no custom characters. You're noticing nothing fancy here. There's no sprites, there's no palette rotations, anything like this. It's very simple. And the memory layout, you might think, well, isn't a fast way to access things, just to start at the beginning and just write, linearly? But it's due to Steve Wozniak's design. It's not like that. There's actually a 3-way interleave where the first line starts at 400, goes to 427, which is 40 bytes in, like you'd expect. But then it jumps way ahead, and you notice that if you kept going on that line, you'd end up at line 8, and then again on line 16, and so it makes it a bit hard to program. And additionally, you'll notice that for a 40 by 24 screen, there's actually some bytes left over to make a full 1K. You think you can access it all, but because the original system's only in 4K, they stuck some scratch RAM for some of the peripherals down there, so the things called memory holes you have to avoid. In text mode, you just go to the line you want, and you write the ASCII byte. But of course, you have to set if you want it to be plain ASCII text, you have to set the hide bit. So or if hex 80. And also the flashing or inverse, it depends on bits 7 and 6, which gets a little complicated. Low-res mode, it's sort of the same as text. It's just instead of writing ASCII byte, you write the top and low nibbles of the byte will give you the colors you want. And down here you can see this 15 colors you can do this to. To actually activate the graphics mode, there's a concept of soft switches. These are memory addresses you read. Sometimes write the later models, sometimes write them instead to set a clear machine state. Usually did this with bit instruction or LDA or SDA, you can any way you access it. Again, there's some complications, but they're not super important for what we're doing here. So you have one that can enable graphics mode or text mode, full screen, or having the 4 lines of text, displaying page 1 or page 2, so you can flip pages when displaying graphics, or you can enable the low-res or the high-res graphics modes. And so to enable low-res manually, you might do this series of instructions. That's 12 bytes, where you have to set those various bits by accessing the very memory locations. Instead, you just call in the ROM. Apple II has some well-defined stable entry points. They're described in the manual. Also, some of the things that are used by Applesoft. In theory, depending if you're using clone system or otherwise, they could change, but it's been long enough past by now that you can pretty much be sure that the common ones you can still jump to. For example, there's a set graphics call that puts the low-res mode, the same as the Applesoft GR command. And it'll set the low-res graphics mode, set you to page 1, split the text and graphics, and clear to black. So if that's what you want, this can save a whole bunch of independent instructions. Now to plot points fast can be sort of difficult because we said we have that weird interleave. The fast way to do this is usually have a lookup table, and then what you do is you load the y-coordinate, you mask off the bottom bit to make it even, and then you look it up in the offset table, and then you store it to a page in a low page as you use an index byte. You load the color, and again, for this you want the top and bottom nibbles the same. You can plot the color. The problem is if you're trying to do 40 by 48 graphics, when you're plotting a point, the top or bottom nibbles, you actually have to load in the old value, mask off the value, or them in because you only want to set the top or the bottom. Sometimes to make things smaller, you can just do what's sort of more of like a 40 by 24 mode, where in that case you just have the top and bottom nibbles the same, and it's a lot faster, but the resolution's a little bit less. So this is a very fast way to access memory. Index against off the 0 page like that. The problem is, you have like 48 bytes here off the top, and if you're trying to size code, this is not going to fit. Instead, you can use a ROM routine. So there's a ROM routine for plotting points. So to plot, for example, to plot a light green point at 1010 on the screen, you just load CC, which is the light green color. You store it to a 0 page address and 30 0 page address. You load the X and Y coordinates into the Y and A registers and just jump the plot. And it does, and then it just plots on the screen. It's small. Unfortunately, it does slow because it does a lot of math to calculate the address. You can do a compromise here. If you're drawing in the same line, there's no need to recalculate the line address each time because it's going to be the same. So you can call the gbasecalc command, which will set up in the 0 page the pointer for you. Calling plot once will also do this. And now you have to make sure the mask in 0 page 2e is right. It's 0FF0. But if you do that, if you call plot 1, it'll plot a point at the current y coordinate with the x coordinate in the y register. And if you do that, if you're drawing like a whole line across, it can be decently fast, but still reasonably compact. There's some other calls you can use that are useful in the ROM for making compact code. Hline will draw a horizontal line from register Y to the value in 0 page 2C on line A. There's a vline, same for drawing a vertical line. The screen command will get the color of a pixel if you want that for some reason. And setcall will set the color to 8 times 17, and that sounds a weird thing to multiply it, but we said the top and bottom nibbles are the same, and you can do the math by multiplying by 17 of a 4-bit value will actually duplicate it top and bottom. So where do we find these ROM routines? Well, the Apple manuals from the old days are actually really good if you can find them online. Also, people have posted ROM disassemblies online for Applesoft and both that and the Monitor ROM, and those are very useful to look for routines that could be useful to you. And you can use some of these in the usual fashion. So for example, here's the 64-byte Doom Flame demo I did. It was 80 bytes. I couldn't really get smaller. But if you notice it's moving, it's scrolling up, just everything up by one line. And the graphics doesn't support scrolling. But in the ROM, there is a routine for when you type text and hit enter off the edge of the screen, it scrolls it up. So what this is actually doing, it's using the text ROM scrolling routine. And since the text and low-res graphics are the same on the Apple II, you can use this routine. It adds a little bit of flicker, but it saves 16 bytes over trying to do things manually. One more thing you can do is page flipping. If you want smooth animations, you can draw a screen and then flip pages. Unfortunately, the ROM routines for low-res aren't page-aware, so you have to manually add things. And in general, it takes about 20 bytes to do this, so maybe not be something you want to do in maybe a 64-byte entry. So high-resolution graphics, they're actually even worse than low-resolution, if you can imagine that. In addition to the 3-way interleaving, each line has an 8-way interleaving going now then, where every 8th line it comes back, but you start 2000 in hex, then skip a K to the end, and then you bump up a bit again. And again, there's memory holes, though in these cases you can overwrite them unlike low res. But it's really complicated to find the address. The graphics mode's 280 by 192 on a mono monitor. It's drawing it's drawing points at that spacing. If you view this on an NTSC color monitor, you get NTSC artifacts, which cause it to form color in roughly 140 by 192. And the way this is even drawn is really complicated. For each 2 bytes, you get 7 color pixels. So each byte is roughly 3.5 color pixels. And when you draw the pixels, the two multiples of 2 bits, 0, 0 is black, 0, 1 is color 1, 1, 0 is color 2, and 1 is white. One interesting aspect of this is adjacent 0, 0s or 1, 1s are always black or white, even if they aren't aligned. So you can sometimes, when you're changing colors, get a black or white fringing between the lines. And additionally, you might say, if a byte or 2 bytes mapping to 14 pixels, black and white pixels, what about the extra 2 bits in the byte? The original Apple II, they were ignored, but then WOZ quickly found out you can use these to set a half-bit shift in the output and change your colors. And so you get the 2 high-res palettes this way, the green and purple black and white palette and the orange and blue black and white palette. You can change this by setting the high bit in the byte. So every 3.5 pixels, you can change the palette. And but this does mean that you have trouble when you're switching colors or trying to have the 2 palettes mixed, and you end up with color clash, a lot like you get, say, on a ZX80 Spectrum type machine. And so because it's so hard to do direct drawing to the screen, often use the ROM high-res routines for this. There's some useful ones. HGIR and HGIR2, these are the same as the commands you get in AppleSoft Basics. HGIR will set the high-res mode, set it to mixed text and graphics using page 1 and clear to 0. HGIR2 will set high-res, put it in full screen mode, showing page 2 and clear to 0. There's an hclear command that will clear the page, either 20 or 40, that's in 0 page E6 to black, or the background command, which will clear it to the last color plotted. There's an H-position command that will move to the x-coordinate YX and y-coordinate A. It takes 2 bytes to specify the x-coordinate because it's 280 wide, so it won't fit in 1 byte. There's an H-plot 0 that'll plot the point at YXA, and there's a draw line to command and a draw line relative to command you can draw with. And some useful 0-page addresses. There's the E6 holds the current draw page. 2627, that's where the current line address stores, so you can do a thing like with low res where you set the line, and once you're in there, you can index into it a little bit faster. And E4 stores the color pattern, and again, this is not 0 through 7 like you might think for picking which color, but it's actually the bit pattern, and so there's a lookup table in ROM you can use to get that. One other thing the Apple II has, it has shape tables in ROM. This is in ROM vector drawing, so you can draw these vectors, you can rotate them, scale them. It also does collision detection when drawing them. And so you can draw or xdraw, or draw just draws it, and xdraw does an exclusive OR. So if you draw it twice, it'll remove it. So that's handy for animation. And you put the shape table you want. You put a pointer to it in 1A, 1B in the 0 page. The scale goes in E7, and when you call the calls, the rotation's in A. And the format itself is a bit too much to go into here, but you can either draw and move up, down, left, and right, or don't draw, but still move. And so you can draw these out, and you can pack up to 2 or 3 of these per byte. It's complicated based on the things. But down below you can see some examples where we're drawing some shapes and scaling them or rotating them. And it can help you draw some high-res graphics fairly compactly. You can also use the high-res routines in unusual ways. Down below here you see a low-res graphics routine, but it's actually using an off-screen texture for doing the drawing. And the way it does this is you use HGIR or HGIR2 to initialize the screen, then drop the low res with a single 3-byte instruction, drop the low res mode. And we can also use the high res background call, it'll clear or set the high-res memory at 4,000 or 6,000, but it's a lot faster than hand coding a memory clear routine. And you can also clear it to a bit pattern. And so we use that to initialize the RAM here a lot faster and smaller than we could have if we had to open code a routine. Some other useful things in Sizecoding, random numbers. The AppleSoft ROM routine has a floating point random number generator. It's not very useful at all. It's also not very random. You can make a relatively compact 8-bit linear feedback pseudo-random number generator in 6502 assembly, around 13 bytes. Often what people do if they need really small random number, roughly random numbers, is just index into the ROM, and it's sort of random enough for star fields and stuff like that. It's more or less good enough. Other things, math, you might say, can we get nice ROM routines for sine, cosine, square root, and all that? And AppleSoft has those, but again, they're complex to use. They're not really that fast, and they're hard to use compactly. So usually you have to waste some space with lookup tables. Reading the keyboard, the way you do this, you read the value at address C1000 in the I/O space. If it's positive, it means there's no key press, but it's negative, the bottom 7 bits of the ASCII, and you can test this easily with the branch plus, branch minus 6502. Once you've read it, you need to clear the keyboard strobe by reading CO10, which will clear things set up for next access. It's ASCII only, so no raw mode, which means only key down events, no key ups. You can't actually get things like controls and things like that are being pressed independently. In the older manual machines, you had to manually hold down a repeat key to get a repeat when you hold something down, but there was auto repeat. This makes writing games really a pain. Sound, there's a plain speaker at CO30. There's no timer or hardware support for this. The only way you get it, you access it and it clicks. And if you do anything more than clicks or like a groaning noise, you have to cycle count, which makes it hard to do compactly. A common expansion, or a relatively common expansion, is a Mockingbird chip, which had AY3, 8, 9, 10 chips for it, behind a 6522 I/O device. So you can, it has in timers for it, and you can do chiptune type music. It's really hard to size code this, though. In general, it takes hundreds of instructions, so it can be hard to get nice music in compactly on the Apple II. One thing I mentioned is the AppleSoft Basic Twitter bot. On Twitter, you can upload 280 characters of BASIC into this, and it will actually run them in an emulator and post the results, and it's a lot of fun. And the interesting thing is, we've been working on this, but we can get up to 144 bytes of machine language into the BASIC payload. And so it's caused a whole bunch of new size coding ideas where we try to optimize things. And it's a different range. It's not 128 or 256, but 144. And on Apple II, it's actually a nice sweet spot for getting interesting demos, so you can check that out. So now some issues you might have when trying to make your size coding product for competition. So getting your executable disk image, if you want it to auto run, in BASIC, AppleSoft BASIC, you use the hello BASIC command by tradition is the one that gets run. And so if you put this print chr screen 4 brun file name, in place of your file name inside of your inside that program and have it saved on disk, it'll automatically run. So you can automatically run your machine code program when it runs. Header size, this is important in size coding. Apple II binary files have 4 bytes of header. It's a 16-bit little endian address that it gets loaded at, and a 16-bit little endian address is the file size. And these are not loaded into memory, so most competitions will let you not use these, at least for smaller sizes, because they're not useful. There's no way they're useful. They're just on disk. In fact, these probably should have been in the file system metadata, but the people designing the file system, is a very early file system. They didn't really know what they were doing. Returning to DOS and BASIC, larger demos, people often want you to check for key press and then return back to the prompt. This is tricky on the Apple II. Most people didn't ever worry about this. You just reboot the machine. If you need to return back to DOS or the BASIC, try not to stomp on the DOS part of the 0 page. And again, that's all scattered around, so it's tricky to do. Try not to stomp on the IRQ vectors that live around 3D0 to 3FF. Try to avoid memory above 9600. That's a little bit easier to do. And then just hope for the best and jump to 3DO, which is where the return to DOS vector lives. Boot sector demos, you want to try that. Apple II had 140K disk. The DOS 3.3 file system, which eventually became the standard, has 35 tracks and 16 sectors, each 256 bytes each. When you boot up the system, starting with the Apple II Plus, it had this in ROM. It would read track 0, sector 0, would be read by the disk firmware by default. And this can be pretty fast. The disk 2 is much faster than loading from cassette, and it's a lot faster also than the Commodore 64. So it's not as slow, and with the right routines, you can actually get much faster. Anyway, the first 256 bytes is loaded into memory in address 800, and then it gets jumps to 801. You might say, what gets loaded to 800? 800 in your file is usually 1. It tells the firmware how many sectors to load. Most people leave that at 1. One additional thing you probably want to do with your demo is to turn off the drive motor. Otherwise, the drive mode will just keep running unless you turn it off. So you have to waste 3 bytes doing this, where you load A from a certain address, and you have to know which slot the disk drives in, which again, you can find out, and it takes a few extra bytes to find that out. It's usually slot 6 on an Apple II. Some people ask about double low res and some of the other advanced graphics modes for the Apple IIe. So you can get 80 by 40, 15 color mode. It's complicated to program. The ROM routines don't help much. There's lots of soft switches and bank switch memory you have to set. The horizontal bytes alternate between main and auxiliary memory every other byte, which is a pain to program, and page flipping is difficult. Still, people use it for some things and can use it for demos, not very compactly though. About those soft switches, so the Apple IIe, you can switch between regular memory in 64K and auxiliary memory in 64K. The problem is when you switch, everything switches, including the 0 page, the stack. You need to have code in the exact same location because suddenly your instruction pointer, your program counter, is in the other auxiliary memory. To make things a little bit easier, just doing graphics, they have a mode you can set where page 1 and page 2, now instead of switching between the 2 pages in memory for graphics access, they switch between auxiliary and main memory. And so that way, you can very easily program the graphics by just switching the page flipping. So instead of switching the pages, it switches between the 2 things you need to do. Some of these more advanced auxiliary bank switching stuff, you need to write instead of read or write to set soft switches, and some of the more complicated ones for the language card, you actually need to do double reads or double writes and more complicated things like that. Some useful ones though, 80 store on is the one that switches to the page switching to main auxiliary video. 80 column on, you need to have the 80 column card enabled to do these modes. All care select on, that's if you want to do the mouse text. And Enunciator 3 got repurposed to enable the double graphics modes. Double high res is another mode. It's 140 by 192, like in high res, but with 15 colors. That's even more complicated to program. And again, page flipping is difficult. Colors are 4 bits, and there's no palette, so you think that'd be easier, just 4 bits. But it turns out that the palette bit still there is ignored, so you have to fit these 4 bits in 7 bits, so they get offset and make it even more confusing. The colors are shifted, and between auxiliary and memory, every byte gets between them, and it's just a nightmare to program. You can still do it though, and people have done interesting things with double high res. Finally, some people are interested in my coding setup. I wouldn't necessarily recommend it to anyone, just what I'm comfortable using. I use Linux with the Nano editor. You know, it's low end, but it works for me. Then I use the CA65 assembler from CC65 project. I have a makefile that makes the things, and it uses a custom tool I have called DOS33FS that will copy my programs to the disk images. And then I test the disk images in the Applewin emulator, which I run under Wine on Linux. So it's a tower of different things in a way here. And finally, once I've tested it, when I'm trying real hardware, I have USB or SD card disk emulators on my various Apple IIs, and so I just copy the files over that way. And that's how I get them working and test it. So that's all for my presentations. Any questions, feel free to email me. You can find more info on this and links on my website here. Thanks.